Good evening, everyone. My name is Prithili Madar. Today I am going to chant Shiva Pashana Mantra. Om Nidhanapataye Namaha Nidhanapatantikaya Namaha Urdhvaya Namaha Urdhvalingaya Namaha Hiranyaya Namaha Hiranyalingaya Namaha Suvarnaya Namaha Suvarnalingaya Namaha Devyaya Namaha Devyalingaya Namaha Bhavaya Namaha Bhavalingaya Namaha Sharvaya Namaha Sharvalingaya Namaha Shivaya Namaha Shivalingaya Namaha Jvalaya Namaha Jvalalingaya Namaha Atmaya Namaha Atmalingaya Namaha Paramaya Namaha Paramalingaya Namaha एतत्सोमस्य सूर्यस्य सर्वलिङ्गस्थापयति पाणिमन्त्रं पवित्रं सद्यो जातं प्रपद्यामि सद्यो जाताय वै नमो नमः भवे भवेनातिभवे भवस्व मां भवोद्भवाय नमः वामदेवाय नमो ज्येष्ठाय नमः श्रेष्ठाय नमो रुद्राय नमः कालाय नमः कलविकरणाय नमो बलविकरणाय नमो बलाय नमो बलप्रमथनाय नमः सर्वभूतदमनाय नमो मनोन्मनाय नमः अघोरेभ्यो घोरघोरतरेभ्यः सर्वेभ्यः सर्वेभ्यो नमस्ते अस्तु रुद्ररूपेभ्यः तत्पुरुषाय विद्महे महादेवाय धीमहि तन्नो रुद्र प्रचोदयात् ईशानः सर्वविद्यानामीश्वरः सर्वभूतानां ब्रह्माधिपतिर्ब्रह्मणोऽधिपतिर्ब्रह्मा शिवो मे अस्तु सदा शिवो नमो हिरण्यवाहवे हिरण्यवर्णाय हिरण्यरूपाय हिरण्यपतये अम्बिकापतये उमापतये पशुपतये नमो नमः धृतगुं सत्यं परं ब्रह्म पुरुषं कृष्णपिङ्गलम् ऊर्ध्वरेतं विरूपाक्षं विश्वरूपाय वै नमो नमः सर्वो वै रुद्रस्तस्मै रुद्राय नमो अस्तु पुरुषो वै रुद्रः सन्महो नमो नमः विश्वं भूतं भुवनं चित्रं बहुधा जातं जायमानं च यत् सर्वो हेश रुद्रस्तस्मै रुद्राय नमो अस्तु कद्रुद्राय प्रचेतसे मेधुष्टमाय तप्यसे वोचे मसन्तमगुं हृदे सर्वो हेश रुद्रस्तस्मै रुद्राय नमो अस्तु ॐ शान्ति शान्ति शान्तिः थैंक यू
A very good evening, everyone. Myself, Shauradip Odhikari. A warm welcome to all our brilliant participants joining us from around the world for today's exciting international webinar organized by Modak Trainer Academy. Today, we are here to discuss a topic that is as fascinating as it is vital: the force of 4 R's in energy resilience. This webinar is our golden ticket to exploring how the 4 R's are more than just buzzwords. They are transformative strategies for a sustainable tomorrow. Now, I would like to share a few words with all of you about our today's distinguished guest speaker. Let's talk about the extraordinary speaker, guest of the evening, Dr. Malabika Basu. Dr. Basu is a name that is very popular in the world of electrical and electronic engineering. She is a beacon of innovation and excellence in the field of electrical engineering. With her cutting-edge research in grid integration of renewable energy sources, power quality control, energy resilience and microgrids, she is paving the way for transformative advancements in energy systems. Dr. Basu has a remarkable academic lineage, having earned her bachelor's and master's degrees from the Indian Institute of Engineering Science and Technology, Shibpur, followed by a PhD from IIT Kanpur. Her journey has taken her from serving as a lecturer at Jadavpur University to becoming an Arnold Graves postdoctoral fellow in Ireland, shaping the energy landscape at every step. She is a senior lecturer at the prestigious Technological University, Dublin, Ireland. Not only she guided over 11 PhD scholars and authored more than 120 research papers, but she has been instrumental in shaping the future of energy research globally. Her efforts have led to the establishment of a world-class power quality laboratory at Technological University, Dublin, backed by over 1.5 million euros in research funding. Beyond her research, she has also made significant contributions as an associate editor for several prestigious national and international journals. And starting 2025, she is going to join the editorial board of the IEEE Journal of Emerging and Selected Topics in Industrial Electronics, a role that highlights her global recognition. Respected Dr. Malabika Basu, Madam, we are thrilled to have you with us today. Your expertise and valuable insights are a beacon of inspiration for all of us, and we are eagerly waiting for your valuable lecture. Before we dive into the session, I want to take a moment to thank each of you for being here. So, without further delay, let's get started. Please join me to welcome our expert, distinguished guest speaker, Dr. Malabika Basu. Over to you, madam. Thank you.
Thank you very much for the big introduction. I don't know if I would be able to satisfy the audience, but I'll try my best. Before maybe starting, I would just put up the slides to share mode so things can be set up on the stage.
Okay, ma'am. Share screen.
Okay, thank you. And Prithili, it was very nice chanting. I really enjoyed, and thank you very much for the wonderful chant.
Thank you, ma'am.
Okay, so it has come. So should I start now?
Yes, ma'am.
Okay, thank you. Om Shri Guru Pyo Namaha Hari Om. Good evening, everybody. I'll just put the screen here so that I can at least see some of your faces. And thank you to Modak Trainer Academy for giving me this opportunity to speak at your uh, academy. Um, I would like to offer my reverential pranams to revered Shami Bimukshanandaji for encouraging me to come up and speak today. Also, I'd like to thank Dr. Gargide, uh, who had been very flexible and accommodating for on behalf of the Modak Trainer Academy. Today's topic has been personal choice because I was a bit worried that what kind of topic would be suitable. I understood that the esteemed audience comes from various different expertise, subject areas, and background. But in 2021, once I was invited to give a talk on energy resilience, that was during the COVID period. And while preparing for that, I found that it has also a general, it can be a general topic of inspiration because resilience is something that we require in all facets of life. So from that perspective, I have selected today's topic on energy resilience, something that could be of general discussion and something particular to my professional area of interest. So hopefully there will be food for thought for every listeners. So I would start with the dictionary meaning of the word resilience that the Cambridge Dictionary provides. And it states it's the quality of being able to return quickly to previous good condition after problems. Or if I go by the Merriam-Webster definition, maybe if I read out the second one, which is shorter, an ability to recover from or adjust easily to misfortune or change. So essentially, resilience is closely related to problem, challenge, stress. And I think none of us can escape from these. So perhaps this is one of the most pertinent word and characteristics that all of us are aspiring to achieve or have. Now, what about the 4 R's in resilience? So it is something related to refusing to give up. And these 4 words are robustness, redundancy, response, and recovery. So that something helps us to face the challenge and then come up with plans. If plan A don't work, what is the plan B? And not to agree to give up so easily. And then accordingly create our response to the challenge at hand and then pave our way towards recovery and get back onto track. And perhaps this is a very generic plan for every challenge. And today we will try to cast it on a global problem and then be specifically going to electrical engineering aspect of it. We will see. So what is the global problem? And this is something related to the United Nations Sustainable Development Goals and the need of it. So in the year 2015, leaders from 193 countries of the world came together to face the future. a call to action to end poverty and inequality, protect the planet, and ensure that all people enjoy health, justice, and prosperity. It is critical that no one is left behind. An aim to transform the world. The world has seen enough of famines, drought, wars, plagues, poverty, not to mention about COVID because in 2015 it was still unknown. They knew that we had enough food to feed the world, but that it was not getting shared. They knew there were medicines for HIV and other deadly diseases, but they cost a lot. They knew that earthquakes and floods were inevitable, but that the high death tolls were not. They also knew that billions of people worldwide shared their hope for a better future. So leaders from all these countries created a plan called the Sustainable Development Goal. This set of 17 goals imagined a future in just 15 years of that the world would be rid of poverty and hunger and be safe from worst effects of climate change and other diseases. It was an ambitious plan, no doubt. With the plan, they were looking to achieve their targets by 2030. And perhaps all of you might have seen at least some of these logos, and they are attached with some particular letters, words, color codes, and icons. Say, for example, number 1 is no poverty, 2 for zero hunger, then number 13 is for climate action, number 4 is for quality education, number 5 for general equality, and so on and so forth. And number 7 is for affordable clean energy, 9 for industry innovation and sustainable infrastructure, 11 for sustainable cities and communities. So what's different about these sustainable development goals? The 2030 agenda and its goals offer a comprehensive vision. So nothing is exclusive or isolated, and one goal will also influence the other parameters. It is also global rather than targeting or limited to developing countries, as was the case for Millennium Development Goals. It is based on values such as equity and respect for human rights. It relies on approaches such as sustainable financing, scientific research and innovation, and monitoring and evaluation. And it requires a new way of working involving intersectoral action by multiple stakeholders. And it aims to strengthen health systems towards universal health coverage. Now, are we on track to meet these challenging goals, ambitious targets? Well, if you look at a glance towards the right side of the slide, where progress assessment for 17 goals has been based on assessed targets, you see the color codes that green is on target or target met. Then next is orange for moderate progress. Then yellow for marginal progress. Then pink is for stagnation and red is for regression. Now, with all these color codes, you can clearly see that the percentage green is not prominent or very prominent in this assessment. Only about 17% of SDG targets are on track. There are about 17% targets are on regression, that is the deep red side. And similarly, about 16% are on stagnation. So in between, there had been some progress, moderate to marginal. So these are about 50% of the cases. So undoubtedly, we have a case for resilience to get back to track in these overarching 17 SDG goals. Now, what are the challenges that has been hindering the progress? One of them undoubtedly had been COVID-19 pandemic, and also the global escalating conflicts, geopolitical tensions had not been helpful. And growing climate chaos are one of the major obstacles. If you look at goal number 13, which is on climate action, you will see that the progress is very, very marginal, and there has been a significant regression. So definitely urgent action is needed. But before going and acknowledging further the problem areas, we should also be mindful of the tangible progress areas which falls within the 17%, that there had been good achievement in reducing global child mortality, preventing HIV infections to a large extent, and access of energy and mobile broadband. So, as you can clearly understand that these 17 SDGs and resilience has to be interconnected, and we have to use resilience. We have to restart our path towards recovery, and we are trying to do that to get back on track. Say, for example, in Ireland and in EU, when we have to write any research proposals, we have to clearly indicate that which of the SDG goals and the targets we are aiming at, and the result of the research is going to impact. So this has been one of the mandatory criteria. So irrespective of our stations of life or professional expertise, or where we are standing at the moment, everyone can contribute to some extent, so that globally we can still try to aim and get back on track towards this noble cause of having a better world for our humanity and living beings. Now, today I would go to the specific of the SDG 7, an electrical engineer's headache. Because of my professional training and the background, I would be most comfortable to talk about this. And also, due to the overall time constraint and the problem is so big, probably we cannot afford to touch about all of the other 16 goals. Now, what is this vision of SDG 7? It is to ensure access to affordable, reliable, sustainable, and modern energy for all. What are the specific targets? That the accessibility should be affordable, reliable, and based on some clean energy services, so that we don't impact on the climate chaos any further. So obviously we have to increase the renewable energy in the global energy mix, and also we require to improve the energy efficiency. So these targets aims at to address the critical role of energy in achieving the sustainable development, including poverty reduction, economic growth, and environmental protection. So within the broad goal, there are several sub-targets and the indicators that shows that, okay, if we want to ensure or work on increase of share of renewable energy, then what are the subtopics or the sub-targets we have to meet, or the target, say, for example, for 7.2, which is to increase the share of renewable energy. So we have to see that renewable energy share in total final energy consumption is also appropriately addressed. So likewise, these targets are divided into multiple indicators. Now, on a page infographic provided by the United Nations, what are the essential challenges? that SDG 7 specifically needs to address. So number wise, or the facts and figures as of now collected, it says that still 675 million people are living in the dark. Unfortunately, 4 in 5 of them are in the sub-Saharan Africa. 1 in 4 people will still use unsafe and inefficient cooking systems by 2030. And worrisome figure is that international public financing for clean energy for developing countries are on the decline. So the funding has to be substantially increased so that we can aim to meet the technological targets to benefit the humankind. So these are few more facts and figures, not very inspired, or not very, what should I say? They are rather depressing, but with the help of resilience, we still aim to overcome these challenges. Unfortunately, in the sub-Saharan Africa, as seen from the right side of the slide, that population without access to clean fuels and technologies for cooking are on the rise, whereas for the rest of the world, things are not that bad. And proportion of population with access to electricity is also very bleak in this particular continent. But share of renewables has seen some significant development, both in developing countries and developed countries. And with that, the world has seen a significant progress of renewable energy being utilized in practice, from a small scale to a larger scale. In about 7-8 years, it has almost doubled the percentage, and in a global sense. Now, what are the challenges ahead? So, to meet the rest of the SDG goals, we have to improve the average primary energy intensity. We have to improve the energy efficiency. And for that, whatever research is done, that requires also funding and investment and political decision support, policy change, etc. And that has to be also very, very much strengthened. So what are the overall observations? That there has been rapid global growth of per capita installed renewable energy capacity with a significant 8.1 compound annual growth rate. There are still significant disparities. While developing countries saw substantial growth, they still lag behind developed countries. Least developed countries, landlocked developing countries, and small island developing states face the most significant disparities with long timelines to reach even current developing country levels. Rebound in clean energy finance is one of the promising aspects, but it is still not up to the mark. And while the number of recipient countries increased slightly, a significant portion of funding still concentrates in a limited number of nations. So there has been uneven distribution. So there has been investment trends that has shifted from hydropower towards solar and other renewables. And there are declining trends in public finance, which is really worrisome. Now, with this kind of progress landscape and the targets, what are the things that we are trying to do, and what is the way forward? So it has been found out that to map the energy sustainability for a sustainable world. Changes in the energy market, investment preference are very essential, and the decisions has to be supported by political bodies, and an appropriate framework has to be developed. And there has been a change in load pattern that has to be managed properly. Infrastructure is going to be more at risk because of more digitization and network, which are of to the advantage as well as adds to the vulnerability. And we have to keep on increasing the renewable energy in the energy mix. So from that perspective, our goal is to develop a sustainable, resilient, reliable grid. And microgrids are one of the very promising options. Now, before going into the microgrids and other details, let's look at the 4 Rs once again, and then perhaps with the examples, it will be easy to understand that how these 4 Rs of robustness, redundancy, response, and recovery can be applied. Things might get a little bit more technical, so I hope I don't lose the audience attention. I'll try my best to keep it into non-technical terms as much as possible. Now, where can I find a microgrid? Before that, if I start with the general definition of a grid, so it would be a sources of conventional power generation coming from big power stations, and then they are networked or connected among themselves to provide the energy for the city, homes, businesses, countrywide. And that is the uh, understanding of a conventional grid. Now, what is a microgrid? Microgrid could be a miniature version of that grid concept. It can start as small as with 3 houses having little bit of solar panels or some batteries, but it can be even in a moderate scale where maybe with solar some wind can be added to that, and there can be some a smaller network within that, and they need not be totally isolated from a conventional grid, or may not require to be built totally separately. They can be inside a conventional grid structure. And microgrids can help the conventional grid, maybe in terms of storing excess energy, or maybe sometimes when there are shortage or outage, then from the storage energy or the additional storage, they can provide to support the voltage or the frequency balance. And like that, now the solar, wind, and other sources of renewable can be integrated into the consumer network inherently, and they can create a distribution system of their own. They can have the grid support where there are available grid support, but where there are no grid support, they can make a grid of their own and be isolated. And this is the vision towards sustainable, resilient, reliable grid, where now the sources of powers are mostly clean and green energy sources, and there is a efficient communication, and the utilization of energy is also in a much efficient manner. So here, if we try to see the 4 Rs, so the distributed generation resources gives more robustness and redundancy or the adequacy. So if some plan A fails, there are some options for plan B, along with the storage systems, which are becoming hugely beneficial in managing the energy demand and the energy availability, and the communication infrastructure and the efficient control systems are helping in R3 and R4 towards the response and the recovery. Now, so typically the features of microgrids will have these four aspects, and this is more of a emoji or the iconic figure. Uh, so when we try to design a microgrid, or when we try to see what are the available resources to us, what are the loads that we have to manage, whether we can uh, put them, club them together, whether we can have grid support, what kind of electricity tariff or management of the economic plans are at place, whether we have to address the protection issues, or whether there are power quality issues, how are we going to manage the cyber security, how are we going to address the availability of the renewables. Say, for example, sun is not always available, wind may not always flow, and still we should be able to get and utilize those powers as best as possible, are the places where there are scope to exercise resilience. Now, the specifics of the microgrids might sound a little bit technical, but maybe I should mention just one or 2 points so that I can build up the case of the research from there, what we do, and that can make more sense. The strategies for successful microgrid operation, we have to consider what are the variability of the renewables that we need to be aware and mindful of. We have to address the low overload or the short circuit ratings or the power rate limits, because the way the renewables are connected, they are through power electronic converters and inverters mostly. So they have their own characteristics and limitation. We have to be mindful of potential for active load control. Sometimes they are to our advantage. Sometimes they also pose some challenge. Say, for example, electric vehicle charging. If we all want to charge at the same time, and that can put some kind of constraints. Whereas if we can manage and distribute our charging times, that can work to our advantage. And that can come under the another topic of energy optimization, load management, etc. And on top of that, we have to be very, very mindful of bidirectional power flows and unit level voltage and VAR support. Why these are important? Compared to conventional grids, power used to flow from only one direction, from the power station towards the load or the consumers. Now, with all the distributed energy resources installed in every place, even every household can be a little generating station, having little solar panels or some micro turbines or heat pump, something like that. So the concept of exclusive consumer is gradually declining. So everybody have the possibility to become a producer of energy as well. So the new term has been developed, which is called prosumer. So being a prosumer, one can generate electricity appropriately, can sell it back to the conventional grid as a little power station, at the same time can consume power from the grid when there is no availability of the power resources in the local small power station. So pictorially, these are the schematic or the diagrams of the microgrids. And for AC microgrid, that is alternating current based microgrids, There are additional power conversion and power quality challenges, by which I mean that the voltage has to come to the appropriate level with the appropriate 50 hertz frequency. That's most of the places in the world that follow that 50 hertz supply frequency, whereas US has 60 hertz and I think Japan has 40 hertz. So if you are taking power from solar, you are taking power from wind, and then converting it to electrical energy. We as electrical engineer, as power quality engineers, have to ensure that everything comes with exactly like if we were taking power from a conventional power station. If we convert our grid systems to DC, then many of these power quality problems, like managing frequency, etc., will not be present. But very few loads at present are directly AC. So that's why these DC microgrid concepts are building up, but still not yet very popular. Now, with all these bits and pieces of challenges that I am presenting now, I would like to give a feel for what different countries are doing, and is microgrid a popular concept or not. Indeed, it is a popular concept, and it is becoming a very a growing market. So in 8 to 10 years time, the projected expansion is very, very promising, provided we get the appropriate funding from the appropriate places. Say, for example, starting with India, microgrids in India, there are more than 10,000 mini and microgrid projects, and there also microgrid market is rapidly increasing. In Ireland, there are state-funded pilot schemes in the southwest part of the country, where different combinations of controllable load, controllable and renewable source are experimented together, and with the coordinated control and communication. There are some Midlands project with significant power rating are being designed and implemented. So likewise, some other stories, Greece, in the Kitnos Island, there are uh, microgrid projects supported from the EU project. There are, in Japan, there are combinations of different renewables with the intention to provide a technology demonstration. In terms of size also, with different sensitive loads. There are another example of from the Japan. Then in several places of US also, there are microgrid demonstration projects. So particularly in island places where big network connection is a challenge, microgrid is a really very promising solution with the available clean and green sources of electricity. Now, there is another concept of microgrid, which is also called, which is called community microgrid. So it is not exactly different from the idea of microgrid, but in terms of ownership, there is a much more ownership among the local people and the local residents. And that's why this feeling of community microgrid is becoming popular. So what it means is that a microgrid managed, the source and the load are completely managed by the local authorities, and it could be a small housing complex. It could be two neighboring housing complex, and they might be interacting uh, among each other. So what are the ways out to have a efficient uh, connection between these kind of microgrids are also an interesting topic of research. So no matter how the distribution of electrical energy is considered or the thought, or thought of. The main issues are that it has to be with more and more clean and green renewable energy sources. And obviously, those connection or the challenges are to be addressed with the help of technology. Now, unlike the conventional electricity usage over the past few decades, electricity market has been deregulated. So now it is not a state-owned commodity or the service in most of the countries. So there are a lot of options to buy electricity from. So price of electricity and how one can buy and sell electricity are one of the important aspects. So there among community microgrids, if microgrids wishes to buy and sell electricity, that's also a possibility. So to understand the resilience in the community microgrid, obviously the vulnerable areas has to be understood first, and also the resilience options has to be checked along, so that the options don't create overall stability of the operation in terms of frequency or the voltage, or create a situation for load shedding. And at the same time, it can increase more and more renewable energy usage. And it's always a good idea to share the goodness with others. So if one has more clean and green energy, how it can be, the excess can be used uh, when others require it, is an interesting problem. Now, with all these aspects and philosophy, when it comes to implementation for engineers, it comes in a layers. First, the basic control or the primary control and monitoring. Then on top of that is the secondary control, and the coordination level is involved. Then on top of that, if we want to add more features, then the tertiary control and the monitoring are there. Say, just for example, the basic control, like how we are going to take the electricity out of the solar panel and deliver at the proper voltage and the 50 hertz frequency, will be matter of local primary control. And if there are more number of panels and many inverters are connecting them, and how the load is to be shared, we have to look at this droop control and active and reactive P and Q control, all in the primary control area. Then if we have a grid backup, or we don't have any grid backup, say for example, if there is a blackout from the grid side, but we have our local energy supply, then if we have a good strategy for that, we can operate in an islanded mode. So that comes under the secondary control. And then if two islanded microgrids want to share their resources, and maybe the storage options, then we have to look into the frequency and voltage restoration. Obviously, we have to look at our protection uh, aspect and the management of the load aspect as well. So, and beyond that, if we want to be even going for more smart management, then what will be the strategy of the coupling issues with other microgrid? If there are some cyber attacks, how do we prevent or protect ourselves? And can we incentivize the customers so that we can manage our load and available resources? These are all aspects of tertiary control. So with the overarching research objectives of resilience and smart community and sustainable living, these are the layers within which we have to design all our control features and the facilities. So just to give a flavor of the technical things, that when the grid connected control are with the power and the reactive power parameters, when it goes to islanded mode, then the control references and the parameters change to voltage and frequency. When we go for a secondary control with the change in the load or the resources, if the frequency on the individual microgrid varies, say from 50 hertz, something happens to 51 hertz. As such, none of the equipment will be at problem. But if we like to add two microgrids, then we have to agree on a common frequency. Otherwise, that will create a problem. So how do we adjust and come to a common problem when there is a no big grid backup is also a matter of research problem. And then we put them in a so-called block diagram and we look at the individual control and then we see at the responses and then we see check the performance, how things are going to operate in a normal stage, in a dynamic or a disturbance stage, etc. So with this simple block diagram, I would like to offer and check the possibilities of having 4 Rs, that is the robustness, redundancy, response, and recovery between two isolated microgrid. So what are the possible combinations that we can think of? Starting with in a normal operation standalone mode. Both the microgrids may be having a few photovoltaics and some loads for the daily usage consumption, etc., are okay to operate on their own without any additional support from outside. Then one of the microgrids perhaps is a bit rich, so having a additional energy storage BESS capacity, battery energy storage system, and that can be handy during the hours, like when it comes to robustness or redundancy. We'll see how. So then the other two possibilities is that microgrid 1 is overloaded, but the good Samaritan microgrid 2 is ready to connect with the microgrid 1 through a path. And then with this common coupling switches, maybe from the additional battery sources or due to the load and the source profile, it can give some additional power to the microgrid 1 to meet its deficit. Now, microgrid 1 also can have the opportunity to serve back or help back in case the microgrid 2 goes into overload mode and for some reason microgrid 1 may have excess of energy. And for that purpose, if there are some pre-agreement that excess of energy can go and store in the battery storage of the microgrid 2 for later use, or locally, whatever are the demand in the microgrid 2 can be used. So this is the example of robustness and the redundancy. Now, if both microgrids are overloaded, that is a possibility with the limited resources of the microgrid. Had it been a grid connected microgrid, then the big grid can provide this additional excess of the power, but that may not be a possibility all the time. But this time we have to look at the resilience aspect, that it doesn't mean always that we will be able to perform to the maximum capacity. But instead of maximum or zero, there is something in between. So the control, coordination, plan, response will be all involving to decide what is the best way to address the challenge. So it might be that if there are some very critical loads, like say hospitals, that should not go out of power. And compared to that, maybe there are some food storage system that also require a lot of energy, but maybe for 1 or 2 hours, if the freezer is turned off, then not too much of damage will be happening. So to make this decision, the control will decide which loads to shed off and which loads should not be shed off. So it might not operate at 100% capacity or efficiency, but it not need to go to a complete blackout. So this is part of the resilience. And obviously, when both microgrids are underloaded, happy days. So there is a lot of redundancy and we can store the energy for our rainy days in future. Now, how does it look in the oscilloscope or the experimental screen? So typically when the two microgrids are on their own, though they are operating around 50 hertz, the standard frequency, they can have a little bit of different profile. That doesn't matter. We ensure that the voltage and the power, etc., are all as per the power quality regulation. But if we have to merge or couple the two microgrids, then we have to ensure that when the two frequencies are joining together, they speak of the same frequency. There is no disparity. So there is a successful synchronization algorithm, and it synchronizes, and then everything is operating as expected. So when these kind of situations happen in the laboratory, there are moments of joy and parting. And also then there is a research element. We try to see that, okay, what others have done already, can we do a qualitative improvement on that? Say this black frequency variation versus this red frequency variation. The red frequency is damping and stabilizing the frequency after coupling in a much faster sense. So this is just an example of what are the what we test in the lab, and how do we validate that something is working properly. So with this, maybe I'm coming to the end of the talk. Just trying to summarize and remember the highlight that for the SDG 7, that is for the energy SDG goal, there are goals and challenges as the other SDGs also have. And energy is something that impacts the society even more so today, because we are becoming so much electrically uh, dependent for every little bit of things. So anything good in terms of energy is going to benefit the community. So I have discussed some of the challenges in the community energy issues, and there are scopes of improving the technology from various aspects. Now, going back to the generic sense, like had it not been into the electrical um, energy related problem, these robustness, redundancy, response, recovery can be applied to other fields as well. So maybe if we talk in a general sense of resilience, the features, when we face a problem, we have to cultivate a belief in our ability to cope. That is R1, robustness. We have to become self-reliant. That is electrically individual microgrids are serving this purpose. We need to stay connected with the sources of support. So from where can we get help? So that is the interconnection with other microgrids. R2, redundancy. Now we have to talk about what we are going through, our challenges. We have to communicate with our friends. So that is the communication through control algorithm. R3, response. We have to be helpful to others. We have to share the resources, be it energy or the other things. So if there are excess generations in case of electricity, that's again R2. We have to activate positive emotion, intelligent decision-based algorithms. So that is a response to recovery. And then we have to cultivate an attitude of survivorship. So we have to protect ourselves adequately. We have to also seek meaning of what it is all about and evaluate the benefit and the improvement, our path to recovery to get back on track. So as I mentioned with one of the examples, that sometimes we may not be able to operate to our maximum efficiency or the maximum possibility, but that should not prevent us from doing something, or what best can we do. So we should not be thinking that if we can do this the best, we should not be doing anything. So as I find this Martin Luther King's quotation to be very inspiring, that if you can't fly, then run. If you can't run, then walk. If you can't walk, then crawl. But whatever you do, you have to keep moving forward. Now, the last word for resiliency today from Thomas Alva Edison: when you have exhausted all possibilities, remember this: you haven't. So never give up hope. But I cannot finish without quoting Swami Vivekananda in terms of problems or the challenges or the failures, and way to recovery and the resilience. Never mind these failures, these little backslidings. Hold the ideal 1,000 times. And if you fail 1,000 times, make the attempt once more. And that is resilience. So that's the last slide of acknowledgements. My thanks to Gargidi for being so flexible and accommodating. And thanks to Modak Academy, Trainer Academy, of course. And thanks to Sudevi for making the connection. Thanks again to revered Swami Vivekshanandaji Maharaj, because without him, I would have certainly postponed today's talks. And thanks to Chandrani for bearing all my ghan. And I must acknowledge profoundly Atmaja for giving very insightful feedback while preparing the talk. And hearty thanks to my past and present PhD students, in particular Dr. Sandipan Patro, who shared the excitement and joy of microgrid research and power electronics experiments. Any remark, comments, feedback, observations, question, clarifications, welcome. Thank you.